and actually publish it in YouTube. So yeah, if you have any objections about it, try to reach me and we will see what we can do. We can blur your name or whatever is what you're going to say. Today we have a very interesting talk by Robert Boedigheimer. Forgive me if I'm saying your name incorrectly, Robert. We all know Robert, most of us anyway, from Pluralsight, from his courses in Pluralsight. But I don't know if you knew that he's also a third-degree black belt. So yeah, you better like what he have to say today. I know I will like it, Robert. Anyway, I don't have anything else to say. I will stop sharing right now. And Robert, the virtual stage is yours.
Okay, can you hear me okay?
Yes, we can hear you, Robert.
Okay, it won't let me start my video for some reason.
It's okay. I will also stop mine to save some bandwidth. Maybe it will be better. Let's see.
Okay, let me share my screen here. And let me know if you can see that okay.
Yep.
Okay, let's get started. So we're going to talk about cryptography.
Robert,
yes.
Can I make a small note that I'm sorry, I forget, we already discussed about it, but I completely forgot. If you guys have any questions, just send them in the chat. I will monitor the chat and pass them on to Robert whenever you feel like it, Robert, probably at the end.
Yeah, either that or you can watch. And if a number of them come up, I don't mind taking them as we go either. So whatever
Super.
works.
Super. Thank you very much.
Yes. So we'll talk about Cryptography 101. And I'm going to give the examples in C# and .NET Core. The concepts apply to virtually any language, any framework. Most modern languages and frameworks have access to cryptographic libraries. So it's more important that you understand the concepts in case you don't happen to know C#. I'm also giving you the code and the slides. So at the very end, I have a link where you can do the download, and I have the .NET Core version, which I'm going to show today. I also have the .NET full framework version. Very similar. There's not a lot of differences between the two. I'll mention on a few slides some things that are different, but that's my Twitter information. And as we talked about a little bit about myself, it's my Twitter, my email, my blog, and again, I'll show some of those again at the end. So what is cryptography? So the cryptography is the science of keeping messages secure. There's really four main areas of cryptography. Most people think about the first one, which is confidentiality. When you talk about cryptography, a lot of people immediately think about hidden data, right? Being able to stop somebody from reading the data. There's also a few other uses. Integrity. So integrity is where I want to verify that the data has not been modified. There's also authentication. So where I want to identify and validate a particular user. And lastly, non-repudiation, where the sender cannot deny later that they sent a message. So we're going to show digital signatures. So all of these things are part of cryptography. And as we look through algorithms and classes throughout this talk, I'm going to refer back to which one of these goals. So it'll be important to have an idea of what each of them means. In .NET, we're going to be using the system.security.cryptography namespace. There's a lot of considerations when you start thinking about cryptography. So the first is, what is your goal? So when I talked about the goal, confidentiality, integrity, what you choose for that will drive the correct algorithms. How much is your data worth? How long does it need to be secured? These come into play with how strong of algorithms you want, how strong of keys that you want. You also need to think about your primary threats. So we'll look at threat modeling, and I'm going to show some examples of what the good guys did, what the bad guys did, how they reacted to each other and changed how they did security. I work full-time on an e-commerce website in the United States. And so I need to deal with all of these kinds of things. And from my perspective, my front-end web servers, I consider them to be compromisable. In other words, There could be a 0-day exploit of my web server, and someone could gain complete access to my machine. That's the stance I take when I think about threats. I want to make sure that if somebody owned my web server, I would still be okay. That's my goal. On the internet, obviously, I care about in transit. So I'm going to use HTTPS, as I hope everyone else is, for their website. I need to worry about them accessing my configuration files. It's possible if they take over my entire web server, they could take a process dump of memory. And in that case, I could have passwords, user IDs, credit cards, anything in .NET that has been stored in a string or a variable that hasn't been garbage collected yet would be available if someone could do that. I need to worry that people could modify my web pages to get them to do, so anything my pages have access to, potentially an attacker would be able to do as well. They can reverse engineer my assemblies, so I write in C#, and when I do a build, it's actually translating or compiling my C# into intermediate language. If you ever take a .NET assembly, I can use ILDASM or other tools, and I can actually reverse engineer back to similar source code. So if you're storing secrets within strings within your C# code, those are things somebody could easily get if they had access to your assemblies. There's company security policies. So my company obviously will dictate some of the rules I have to follow from a security and cryptography. There's regulatory compliance. So because I take credit cards on my web server, I need to comply with PCI. So all of these things come into play as I think about security and cryptography. I also want to use layered defenses. So I've got firewalls, I've got web application firewalls, I've got code reviews, I've got then within the code, I'm going to build up multiple defenses to make it harder for someone to attack, right? I mean, the only completely safe computer is shut off in a lead box in the corner, right? I need to be able to run stuff, so I need to trade off the benefits with the security. So I'm going to think through layered defenses. If you take nothing else from this session, don't try to write your own cryptography. So I've run into people that say, you know, I don't want to use AES or one of the built-in algorithms because everyone knows that. I think I could write something myself that no one would know, it would be secret, and that'll turn out okay. And history proves that that just doesn't turn out okay. It would be extremely rare. Maybe one of you is into cryptography and you know a lot of information about it, or you work with cryptography. If you do, you probably wouldn't be at a one-on-one talk, right? So generally, I'd say don't write your own cryptography. That's my main message for today. There's good stuff built in, and we'll talk about where you can find it. And I want to mention this within .NET just because it wasn't that easy to find. There are suffixes on the classes we're going to talk about. So I'm going to talk about AES later, which is a symmetric algorithm. There's a class called AES managed. That means in the .NET framework world, that meant that all of the code to implement that class was written in a managed language like C#. If it ends in CNG, that means that the class is just a simple wrapper around Windows Cryptography Next Generation, which is on the more modern Windows systems. If you use Crypto Service Provider, that's a wrapper around Crypto API, which is available on older versions of Windows. So it meant something in .NET, which one of those you chose and why. For instance, one of the markers was if you needed to be FIPS compliant, which some government work in the US needed to be FIPS compliant, you couldn't use the managed suffixes because they were not certified to be FIPS compliant. So like I said, in .NET Framework world, these things mattered. It turns out in .NET Core, all of these wrap the OS libraries. So .NET Core is obviously running Windows, Mac, Linux. So these libraries now don't, you know, the CNG and Crypto Service Provider wouldn't even exist in a non-Windows environment. So they took all of those and wrapped them around the OS libraries. So I'll show you later. I just have dropped use of the suffixes for the most part, but I wanted you to know if you're looking at someone else's code, what that means. Lastly, because it's cross-platform and because it's wrapping OS libraries, Sometimes those are not available. So you should check this bottom link if you're going to use a feature. They've got good availability across Windows. You may want to make sure that the class you want to use, if you're deploying to Linux or to a Mac, that it actually works on that given platform. So you can check that out. There's a good grid on that URL. All right, so we're going to jump in now to the first area of cryptography, which is hash functions. This is used extensively throughout cryptography, as we'll see. And the idea with a hash function, it's called a one-way function. It's very easy to compute. So I've got this string on the left-hand side. A hash will compute and get down to a fixed size representation of this on the left. It's very easy to compute in the hash direction. It's hard, hopefully impossible, to reverse that algorithm. So algorithms have various strengths. You want it to have the property that it's impossible, extremely, extremely difficult to do a reverse. So those are the kind of hash functions we want for cryptography. So again, once I compute the hash, they often call this a data fingerprint or a digest. We're going to use hash functions for integrity and for authentication. In .NET, there's an abstract base class called hash algorithm, and then the actual algorithms we use derive from that. So I've listed a few of them up here, and I'll talk to each of these. So the first one is MD5. If you hear about a lot of data breaches and passwords and cracking passwords, MD5 is often mentioned with that, and that's because it's no longer considered secure. So I left it here so you knew that it is part of .NET, but I don't recommend that you use that. In .NET, you also have access to they're called the SHA, secure hash algorithms. The first family of those were the SHA-1, and that also is now considered broken. So recent PCI compliance in the last few years said you can't use this anymore. It's not considered secure. The next family is called SHA-2. Those are what I'm going to show you today. The differences in these numbers are the number of bits. So when I talked about every time I hash, if I use 256, the result of the hash will be 256 bits, or 384 or 512. There is actually a SHA-3 family. So NIST ran a competition. It's a standards organization. They were looking and said SHA-2 is similar to SHA-1 and how it operates. So they wanted to have the next set of hash algorithms already vetted to make sure that they were going to be secure. So they ran a competition for SHA-3. They've actually chosen a winner for that. It turns out that .NET does not currently have an implementation of that SHA-3, so I don't list it here. Again, from a company policy standpoint, my company and my personal stance is I don't want to use a lot of third-party libraries if it's available in .NET. So the SHA-2 family of hashes is still considered secure. So rather than go get a third-party SHA-3 implementation, I'm going to stick with the SHA-2. In addition to normal hash functions, you also have keyed hash functions. And that takes not only your data, but also a secret key to do the same hashing. And we'll see why that matters in some examples we've got coming up. So let's just look at a simple example of hashing. So I have .NET Core. I'm using Razor Pages. So I've just got a page here. And what I want to do is take this plain text and compute the hash of it. So as I said, I use SHA-512. That's the production hashing algorithm I use today from a security perspective. I don't have any suffixes on it like we talked about in .NET Core. So I can just create an object of this class. Then I'm going to actually compute the hash. So what you'll notice in .NET, all of the .NET cryptography operates on byte arrays, not strings. So as a .NET programmer, I'm constantly using strings, ints, different types. I need to convert that type into a byte array. So there's lots of different ways to do that. In this case, I'm going to choose, there's various types of encoding. I chose to use UTF-8 encoding. UTF-16 is popular as well. In the case of what I'm doing here with hashing, it really doesn't matter what I choose because I'm only using it for myself. Later on, when we start getting into encryption, if you're working with another partner, this is one of those things you need to agree on. If you don't encode it the same way, they won't be able to use the data. So in this case, I just called the get bytes. That gives me back a byte array representation of this plain text. And then I call compute hash. And as I said, I get back a byte array. So I give a detailed explanation here about what that byte array looks like. By default, it's 64 bytes, and each byte would get represented. I chose to represent it in hex with dashes. So now that I have a byte array, typically I want to show it on the screen or put it on a URL or something. So I just chose to convert it into hex. And it turns out .NET has a bit converter class. So when I call that passing the byte array, I get back something that looks like this. And I chose for my uses just to strip out the dashes. So if we want to see what that would look like, here's my string. And that's what it hashes to. Again, just a hex representation of the hash value of that string. So it's pretty straightforward to use. If I were to uncomment and take this much larger string, when I run the hash, it'll obviously be a different hash value, but the size will be the same. So the size of your hash here is dependent on the algorithm you use, not the size of your input. Okay? So that is hashing. So where would you use hashing? So here's a good example of a practical use of cryptography. So if you've been to websites that if you look at the URL, it'll have customer number equals 123, for instance. As developers, we know that's probably a sequential ID number. And we also know we can see it on the URL. Often I could go up and change that 123 to say 124. And suddenly I might be looking at another customer's data. Right? That's a big problem from a security perspective. So I want to be able to ensure the integrity of that query string. In other words, I want to make sure when the server handed it to the client and the client comes back, that they haven't been changing the URL. So that's the example we're going to look at with hashing here. So again, I will show you a quick example of what this looks like. So I have a link here. If I click it, you'll see here's the query string I wanted to send. A equals 1, B equals 2, C equals 3. It's just some information I'm passing to this page. Well, what I want to do is make sure that you can't come up here and do this, right? Change that value, hit enter, and be able to see stuff. Now, I'm going to warn you throughout the talk, I would never have this set up this way in production, right? I would not let you see a detailed error screen on my production servers. That just tells hackers things I don't need them to know. I'm doing it here for demo purposes so you can see what's going on, but just be aware that isn't something I'd really have. And you can see the query string hash values don't match. So how does it do that? I have the query string that I want to use, and I'm just going to compute a hash. So I created a common function we'll use throughout the rest of this talk, where I can pass some data. I can tell it what kind of encoding to use, hex or base 64. So you can look at this later. It'll look very familiar. If I'm not using a key, it just does the hashing you saw before. So again, that's how it's set up. And then if the page that uses it, in general, again, I would write this in a common method, and I'd find a way to apply it across all my pages. But for the demo, all I need to do is take the query string, in this case, A. I'm going to pull off the query string, and if we walk through the code here, I'm taking the hash value that was sent, which is here at the end. I'm going to peel that off. I'm going to get the query string off the URL. I'm going to recompute the hash of the query string, and then I'm going to compare the two. In other words, I'm going to run a hash of this and compare it to what the hash of what I originally sent, and I'm going to notice that they don't match. If I think like an attacker, what would I try to do? I'd probably take the hash off, still going to fail. So this is where the keyed part, when we talk about layered defenses, this is where the key part is important. So if you look at what I used, I passed in that I wanted to use a key. So if I go look at that method, what that's doing, it's using an HMAC 512. And then here's my key. Now again, I'll give you a warning. This isn't where I would store it on my production server, but for demos, I want to be able to give you a key. So what does this thing do? Well, this makes it hard, right? If I were an attacker, I could come out, if I saw what you were doing, and I saw that I couldn't tamper with your query string, I would guess that's a hash. If I took the size of this, I would know it's a 512 hash. There aren't that many 512 hash algorithms. I could go calculate for myself what the value would be if I used A equals 2, B equals 2, C equals 3. And if you look in the code, I won't demo it here, but I created this hack tamper proof, and I did exactly that. I said, well, I know how to compute a hash too. Here's the hash value. Then I would take that hash, replace this hash, and I would be good to go. Well, the reason that won't work for my poor attacker is because I'm using that key. So I've made it more difficult, right? Now, not only do they have to guess the algorithm, understand what I'm doing, which normal people won't, they'd also have to compromise my web server and gain access to the key. So it's not impossible, but it's certainly more difficult. That's some of the layered defenses we talked about. So where else do they use hashing? So it's very common to hash passwords. So we're going to get into encryption later. But I used to do research when I was in college, and I was on Unix at the time, and Unix decided when it was implemented, they didn't want to encrypt your password. In other words, you gave them a password, they could have encrypted it and put it in their password file, but then when they needed to decrypt it, they would need an encryption key. So they looked at hashing and they said, why don't we hash your password? So when you type your password when you register, they hashed your password and they stored it in what was called Etsy password file. So I had my username, and instead of having my password, it was a hash of my password. And they were so confident that this was a great idea, they made that file readable by anybody. So anybody who had an account on that Unix system could pull that password file and see every username and their hash passwords. And they did that because they thought it's impossible to reverse a hash. Given a hash password, you can't figure out the password. The problem was they didn't think as an attacker. So what does an attacker do in this case? They're going to guess what your passwords are. And what they did back then, and still do today, they pre-compute the hash value of every word in a dictionary. Or today, you have social media, everything you say about yourself that's publicly accessible, spouse's name, kid's name, dog name, where you work, any of that. I'm going to try to hash all that stuff I know about you, hoping that that might be your password. And back then, it was about 60 to 80% successful that they would find words from the dictionary. So I'll show you what that looks like in code. So the simple hash passwords was just, here's the password I found from that. This is the hash value I pulled out of that file. This is a very simple example. I'm just pre-guessing what some of the words might be, computing the hashes of them, and then just seeing if I get a match. So if I run that, you can see it turned out that that is actually secret. So that's how people attacked it. So when they came back as the good guys, they said, we need a way to protect against this. So why don't we add something called salt? So the idea with this is they would generate some unique random data for each user. So each user has a different salt. They would take your password and your salt value and compute a hash of that and store that in the password file. So this was better because now if I'm an attacker, I can't attack the whole password file at once because I had pre-computed every dictionary word. Now I need to do every dictionary word along with each user's salt. So it just made it more difficult to carry out an attack against the whole password file because it takes me a long time to do this hashing is the goal. So it worked great. It's true, it made it more difficult to attack the entire password file. But if you think about it, salt didn't really help protect an individual's password. So what people did is they would go attack and say, I'm going to find the admin user, take their hash password, and then I only have to pre-compute the dictionary with that salt, because if I can get it as the admin password, it's game over, and I have access to everything else I want. So it was better from a layered defense standpoint, but still not good enough. I'll show you briefly what that looks like in the code here again. So I generated some salt for each user. In my case, I'm doing it each time. This would actually happen when you registered. I would get salt for you, and I'd store that salt for you as a user in the password file. So the important part of generating salt is you need random data. So if you think about computers, computers are really good about running instructions. They're not so good at coming up with random things. And you'll look, most frameworks have a random number generator. The problem is they're really not that random. In .NET, the best thing we have available is this. So it's what's called a cryptographically strong random number generator. So again, it's not perfect, but it generates the best randomness we can do given .NET and the platform we're running on. So an interesting aside, if you're familiar with Cloudflare, so Cloudflare is a huge internet provider. Lots of the internet traffic goes over them. They needed random data for some of their stuff. They actually, I think it's in California, they have a wall of lava lamps. So if you've seen lava lamps, physical lamps that have the lava oozing up through them, they actually somehow use that wall of lava lamps as their random data. So when they need random data, they are able to access that in some way that gives them the randomness they need, which is better than computer randomness. So again, I just do a compute hash like I did before, but now instead of passing just the actual password itself, I actually pass the salt as well. So like I said, that was better. Modern systems go further and do something like this, where not only do they use the salt, they actually have another piece of random data. You can think of it kind of like a key. Again, this is something that if you tried to attack me and you could see the password file, you could see my user ID, my salt, and my hash password. You still need to somehow get access to this. So again, it's just one more layer of defense. So what do modern password systems honestly do? So they use techniques like this. In .NET, it's called PBKDF2. And basically you can think of it as a hash function. So there's other ones like bcrypt. Again, it's very popular for doing password hashing. It's just not natively available in .NET. But the idea with this is I'm going to compute a hash, but these functions let you control how slow the hash algorithm runs. And when you first hear that, you think, why in the world would I want to make that slow, right? Well, the idea is, so I'm a Led Zeppelin fan, so that's not a real password I would ever use, but for this demo, I've got some salt. What I can do using this PBKDF2, I give my password and the salt, and then I choose how many iterations I want to run. So what I'm trying to do there is I want to make it slow enough that it makes it hard for an attacker to pre-compute the whole dictionary. If every hash is expensive, it's difficult then to take the brute force attack. It's just going to take them a really long time to calculate all the hashes they need. But I also need to run the same hash when people log into my website. So I have to make it not 10 seconds long. I need to make it probably like a second maybe, because every customer who comes back is going to pay that second toll just to get the hash, but I'm trading off how hard it is. And then over the years, as computing gets better, I would have to come in here and change my iteration count and make it higher. And then when I do that, my hashes are going to change. So the idea is conceptually just, if I run this, the bigger the number I have here, the slower it is, and I'm doing that intentionally to make it hard on the attacker. Okay. Now we're going to get into some of the normal cryptography for encryption. So I wanted to talk about some of the industry terminology. So the first one is plain text has your original data. So this is what you want to encrypt. Encryption is the process of obscuring that data so it's not readable. Ciphertext is the actual encrypted data. Decryption is the process to get me back to my original data. The cipher is the algorithm I'm going to use for performing encryption and decryption. And I'm going to use this for confidentiality. So like I said at the beginning, this is what most people think about when you say cryptography. They think, oh, you're taking a credit card and you're going to make it so people can't read it. That's what this is. So the first class of algorithms are called symmetric algorithms. So we'll look at the diagram first. I'm going to take plain text. I'm going to encrypt it using a secret key. I have my ciphertext. When someone wants to decrypt it, they're going to use the same key. That's why it's called symmetric. It's the same key for both encryption and decryption. And then I'm back to my original plain text. The main attack against this, if you pick the right algorithms and there's not flaws in the implementation, the only way an attacker can actually attack something like this is to use brute force, which just means they're going to try every key, starting with the first one until they run out. So the difficult part of this algorithm is key distribution is difficult. So they're fast, but if I wanted to use this today, and let's say I look in the chat and one of you says, hey, send me a secret message, we kind of have a problem, right? Because I want to send you a secret, but in order to do it, I need to give you a secret key. Well, I already can't send it to you securely, so you kind of end up in a difficult spot. So just be aware, symmetric is great, they're fast, but this key distribution is going to be where we're going to have problems. There's lots of different algorithms available, some of them in .NET. There's a ton of others. I'm going to focus on Raindoll, which is the AES, the Advanced Encryption Standard. It's government approved for us for US. It's used by most companies, most products. You'll see AES is used. In .NET, there's also DES, which has now been broken, so certainly don't use that. There's triple DES, which is considered better and still secure, but again, I'm going to focus on AES for this. So in .NET, these algorithms are called block ciphers, which just means I'm going to take my data, I'm going to pick a block size, it's going to split my data into that size pieces and start doing encryption. So if you think about that, if I have 256 bits, whatever my block size is, my message is not going to just perfectly fit into that last block. So for that last block of data, I might have one character. I need to fill out the rest. That's where padding comes into play. So I'm going to recommend you use ISO 10126, which just says pad the rest of that block with random data. When you think cryptography, anytime you can make it more random, you're going to be better off, and I'll show you why that matters. AES also supports different modes. Here's two of them. There's a lot of other ones. I'm listing CBC is what I recommend you use. It's very popular. We don't want to use ECB, and I'll show you why. ECB just means take the first block, encrypt it. Take the second block, encrypt it. So if I keep encrypting the same thing one time versus another, the ciphertext is always going to be the same. What CBC says is I'm going to take the first block and encrypt it, and then I'm going to use the result of that as input into the next block. So it adds a little random data when it encrypts the next block. So if you think about that, what does it use for random data for the first block, right? That's what they call the initialization vector. So initialization vectors are just random data you need to seed your first block. Curiously, I'm not mathematically inclined with these algorithms and such. The initialization vector does not need to be a secret. So when I encrypt something with symmetric, I'm going to encrypt it. I'm going to get a unique IV. I'm going to get the ciphertext. I can send you both those things in an email or however I want to give it to you. When you receive it, then it's fine that the person can see the initialization vector. That's not a risk to these algorithms. However, never reuse an IV, because if you use the same IV for this encryption versus another, you've lost some randomness, right? people can start to learn patterns. So again, the important part is just never reuse that. So let's look at how symmetric would be implemented. I will show you the page first. So if I do that and hit encrypt, you can see I've got some ciphertext. Here's the initialization vector. So here's the important thing. Every time I hit encrypt, you'll notice the ciphertext changes every time, even though it's the same value. That's because it's using a unique IV each time. And then when I decrypt, I get back to the plain text that I started with. So from a code perspective, we'll look at the encrypt. I need to first create a cipher. So I just wrote a common function because both my encrypt and decrypt need it. I'm using just AES. I mentioned those other suffixes here, managed and crypto service provider. I've given that up for .NET Core. I've listed what the defaults will be. So I want to switch it to be a little better padding. So instead of the PKC27, I'm going to use the random data. The other thing you'll notice, I have my key here. Again, don't just put this in your direct code. We'll talk about key storage a bit later. But that is my key. If you want to see, all that is random data. So if you look in the code I give you, there'll be this get bytes. That is just using a random number generator of the proper size to give me back a key. So as you need to generate keys, you can just run this. This will give you a good key to use. But again, once I have the cipher, every time I call to create a new cipher object, it automatically makes a new initialization vector for me. So as long as you make a new instance every time, you'll automatically have a new random initialization vector. And then I do these lines. I'm going to create the encryptor. This should look similar from before. I need to take my string and convert it into a byte array. And then I do the line that does the actual encryption. And in this case, I just wanted to show you another popular way to take byte arrays back to strings is use base 64, which you'll notice base 64s end with these double equals. So if you're ever looking at stuff that's encrypted, I can tell right away that's base 64 encoded. So the other thing to take away from this, as I was saying, .NET implemented AES. This is open source. Security people have reviewed this. Lots of people use this. Again, don't write your own, right? And if you look at how much code that is, minus the stuff I have commented out, it's really not a lot of code. You're getting strong cryptography with not a lot of code. It's easy to do in most languages and framework, including .NET. So let's go back to why, even though I have AES, you still have to think about your modes and your padding. So let me switch this to be, I'm going to shut my web server down for a moment. I'm going to switch to use the modes you shouldn't use, the ECB and the zeros, because again, this will just encrypt a block at a time and the end padding will be zeros. So my build worked. So let me start up my web server again. And what you'll notice if we go run this again, I'll hit encrypt. What's different here? Well, the IV is changing because the cipher automatically makes a random one, but because I'm using the ECB mode, it's not actually being used. So this is the same every time. So if you're communicating with someone and you're only sending yes or no or a few values, this won't take them long to figure out and see patterns. So that's why that's a bad mode to use. So again, it is good cryptography. AES is solid. These are modes that you just want to make sure you don't use. So we talked about symmetric algorithms. Now we'll talk about asymmetric. So the idea with the symmetric was I had one shared key. The idea with asymmetric is everybody who wants to communicate creates a public-private key pair. The bad news about these algorithms, they're about 1,000 times slower than symmetric. The good news is it gets somewhat away from the key distribution problem. And I'm saying somewhat because if I wanted to send one of you in the chat and said, hey, I'm going to send you a secret, I could have you paste your public key into the chat. It's okay for people to see your public key. With that alone, they can't figure out your private. So as long as you keep your private hidden, you won't have any issues with people compromising things. So as long as I trust that I got your public key from the right place and it's actually you, so if you type that in the chat just now and we're running the, the Zoom chats over a secured channel, I would be able to go take your public key. I take the plain text, I encrypt it with your public key. Now I have ciphertext. Now no one else can decrypt this, including me. Even when I have that ciphertext, I don't have your private key, so I can't decrypt this. Only the person with the private key can do the decryption, in which case they do the decrypt and get back to the original. So that's the idea with asymmetric. There's a few classes built into .NET. I'm going to focus on what's been used historically, which is RSA. So if we look at the asymmetric folder, so I also have a create RSA key pair in here. So if you just go run that, I'll just show you what that looks like. It's going to create RSA key pairs. This is the public private key in that case. Here's the public. So I talked to whoever I'm sending this to. They gave me their public key in order to do the encryption. So let me pull up the actual web page here. Do Robert again, encrypt it. I'll do a decrypt. I'm back where I started. I create a cipher like I did before. So this is just RSA. And then I'm telling it to read in the public key that I want to use for this encryption. So obviously, if I wrote this in a library, that would be a parameter. But to show you for the demo, that's somebody I want to send to's public key. Same steps we've seen before. I need to convert my plain text to a byte array. I can then do the actual encryption. It's important that you use this padding. So there's various ways to pad RSA. This is the most secure of the choices here in .NET, so make sure you use that for your padding. And then again, I have ciphertext in a byte array. I'm going to base 64 it just so I can display it up here on the screen. So again, really pretty straightforward code, and I've got asymmetric encryption with someone. So where would I use this? So we talked about, let's say I need to take credit cards on my website. I don't want to, so first of all, I can't use hashing, right? I need confidentiality. If I were to hash your credit card, that's a problem because I won't be able to ever reverse it and get your credit card number back. So I want to use confidentiality and I want to use encryption. So in this case, I'm going to generate an RSA key pair because if I used symmetric and I used a secret key, that would mean I'd have to store a secret key on my public-facing web server, which I told you I consider to be compromisable. So someone could potentially attack my web server and gain access to that key, and that would be a problem. So rather than do that, I'm going to use asymmetric. I'm going to generate an RSA key pair. I'm going to put the public key on my web server because if someone stole it, no harm done. That's something that the public can see. I'm going to store the private key somewhere behind my firewall on an internal, very secured system that only that machine has that key. So before it talks to the credit card processor, that's the only system that can actually do the decryption. The other thing I didn't mention for asymmetric is it's meant for small amounts of data. Not only is it slow, but there's limitations in how large you can actually use asymmetric for. So in the case of a credit card, it's really small. So you can imagine I'd come out here and type in, obviously not a valid credit card, hit encrypt. Now when I have this, I could store that encrypted data in a database or whatever I need to do with it. Eventually, I'm going to copy this. It ends up needing to go to our processor. My internal system could take that, and it has the private key, so it could do the decryption and get back to where it started. So again, I've avoided the whole key storage problem from the perspective of I'm not using a secret key, I'm using a public one, and it's a good practical use. Nowadays, a lot of credit card processors actually will give you they generate a public private key pair specific to your company. they give you that public key. So as soon as you encrypt it, nobody in your site can decrypt it, only the credit card processor. So that helps reduce risk because as a company, I wouldn't even have access to the private key. So now that we've seen hashing, we've seen confidentiality, we're going to talk about integrity and non-repudiation, which is digital signatures. So the idea is I want to, again, I pick one of you out of the participant list and I say, hey, I'm going to send you a contract. What we'd like to have happen is you'd like it to be, I send you the contract. You would like to make sure that in transit it didn't get modified. You'd also like to be able to prove that I was the one who sent it. That's what we're going to get from digital signatures. So by default, digital signatures, what you send does not have to have confidentiality. In other words, I could send you a contract. Anybody could read it if that's okay. In the case of this demo, I decided to do all of it. So I'm going to take some data, I'm going to encrypt it, then I'm going to digitally sign it. That way I can send both of them to a partner, and that partner can make sure that nobody saw the data wasn't modified, and they can prove that it came from me. So if we look at the diagram here, I've got my plain text. So I'm going to do the same asymmetric encryption that I did before. I'm going to take the receiver's public key and do the encryption. So this is exactly what we just saw, right? That's asymmetric. Now I have some ciphertext that nobody can read. The way digital signatures work for integrity, I'm going to compute a hash of that ciphertext. And then I'm going to encrypt that hash using my private key. That's the digital signature, because when you get it, you'll be able to take the hash that was sent, look at the ciphertext, prove it hasn't been tampered with. You can use my public key and prove that I was the one who did the encryption, or the signature in this case. And then once you have that ciphertext, you know it hasn't been tampered, you know that I was the one who sent it to you, you can use your private key and decrypt it, and everybody's happy. So let's look at what that looks like. So as the sender, this will look pretty familiar. I've got the receiver's public key. Here's my public-private key. Again, don't do this in a string in production. I'm going to create two different ciphers, the one that I need that has my keys, the one the receiver needs. Here's my super secret credit card that I want to protect. I'm going to change that into a byte array. I am going to use the asymmetric using the receiver's public key to do the encryption. So this is exactly what we just saw, right? I'm just encrypting that secret with the receiver's public key. This is the part, we see hashing again. I'm going to use that. I'm going to compute a hash. This is the magic of the digital signatures. I'm going to use my own cipher, which has my private key. I'm going to tell it to use SHA-512 and tell it to create the digital signature. And then in my case, in this example, I'm just sending that data back and forth to my partner on the URL. So if you see here, I've got my secret data. So here's my confidential protected data. And then if I were to go over on the URL, it also has my signature. And I chose, when I put it on the URL, I did base 64 encoding. I did URL encoding to make sure there were no special characters that, I could have chose to do hex. This is where the agreement part comes in, right? The person on the other end has to know how to do all of this same stuff. So I'm not going to walk through it here, but you can look at what the receiver has to do to make sure they got it all. And again, what I would take away from this is that's a lot of power. We've just done safely encrypted, so it can't be read, made sure it couldn't be tampered with, and proved it came from me. And we did all of that with basically that amount of code in .NET. So that's pretty powerful. Again, a testament to what you have access to if you use it correctly, and also why you shouldn't try to write this yourself. So that is digital signatures. I'll mention another place where you can see all of this stuff come together is HTTPS. So I hope you're using HTTPS for all of your websites to make sure that your data is encrypted and safe in transit. If you're familiar with how HTTPS works, as a web provider, I'm going to go get a certificate. So I create a public-private key pair. I send the public key to a certificate authority. So a certificate authority is like Let's Encrypt or some of the paid ones. They are going to digitally sign my public key in addition to my domain and some other information. I will then host this certificate on my web server. So when a browser comes, they type in my domain, they're going to get my server certificate. Browsers have a hard-coded list of certificate authorities that they trust. So as long as, and I'll just say Let's Encrypt is what I use. It's free and well-known and very popular. The browser knows Let's Encrypt is trustworthy. They signed my public key, so I can trust that's the right public key for this domain. Now, we don't want, as a browser and a server, we're going to send a lot of data back and forth. We don't want to use asymmetric because it's too slow. So what we do is the browser gets the server certificate, it takes out its public key, it generates a brand new symmetric key to use. It encrypts the symmetric key with the server's public key. So when the server gets it, the server can decrypt it, get the symmetric key, and then both the browser and server talk to each other using symmetric algorithms, which are much faster. So we've handled multiple issues here. We don't know each other at the beginning. We don't know how to trust each other. We've used digital signatures to get a public key from the server so that I could transmit a symmetric key. So that's kind of the underpinnings of how HTTPS functions and how it relies on all the things that we've talked about so far. I'll mention key sizes and storage. So the key sizes, when we talk about AES, symmetric AES supports 128-bit, it supports 256 bits. If you look at attacking AES, someone's going to brute force and try every possible key. So the longer your key is, the more they have to try in general. The difference between 128 bits and 256 bits is not just twice as hard. It's exponentially harder the more bits you add. So I use 256. I've run tests, if you don't believe it. Run tests with the two different key sizes, and you'll notice it's very small difference from a performance perspective. I need the security, right? We're doing this because we need it to be secured. So I just choose the highest 256. Asymmetric RSA, the top is 4096. Don't look at these two related to each other and say, well, RSA is a ton more. The bit size and talking about bigger bits, they don't transmit across the two. Just use the highest that you can use within the particular type. I'll admit, key storage is by far the worst. When you talk about cryptography, it's trying to store secrets securely, from my case, on a web server that I know someone could own, is a problem, right? Various places, you know, depending on where you deploy this, you might have Azure Key Vault, you might have all sorts of options. I mean, all of these things are better than putting it in a string, but you also have to consider that each of them have particular weaknesses, which is why when I talked about credit card numbers, I'm going to instead store a public key on my web server and take myself out of the whole game. I don't need to worry now about it being compromised just because it's not actually a secret. So in summary, don't write your own cryptography. I mean, no matter what language and framework you use, you're going to have access to good algorithms. Like I said, I use trusted algorithms and implementations. I'm not going to go to somebody's blog and they say, hey, I made up a new symmetric algorithm that's twice as fast as everybody else's and it's totally secure and pay me this much. I'm not going to do that, right? I'm going to look for trusted algorithms that have been vetted good implementations that have been vetted. You want to use hashing when you want to validate integrity. So again, as you think about things, passwords are good, for instance. You could use encryption to do a password, but you don't want to because, again, you have a key management issue. If you use hashing, you don't have to worry about storing, in general, the key unless you're using keyed hashes and such. Use symmetric algorithms unless you have special needs. So symmetric are a lot faster. If you're able to use symmetric, that's what most actual encryption is using. But use asymmetric when you need digital signatures, key exchanges, things like that. And again, think of your threats. So think of your system. You know, you go back to the Unix creators. They thought hashing just solved the problem. There's no way to reverse it. They believe that, therefore there can't possibly be a problem. They hadn't thought through, how would an attacker react to this? How would they poke holes in what I have? So you need to think like that and decide what countermeasures you need. We mentioned I'm a Pluralsight author. I've got 9 different courses. I do a lot of work with Fiddler, so I've got some Fiddler courses. I have Introduction to Cryptography in .NET, which goes over a lot of this along with history and some more details. If you're interested in cryptography, these 3 books in the middle get into a lot of the very specific details about how algorithms are implemented. I've tried to read, say, AES and figure out all the bit shifting, exactly how it works. Not something I personally care about. I'm going to trust the cryptographers are implementing the algorithms right and it's being vetted. I've used these books more for, they do get into that, but they also talk about things like why you shouldn't use ECB mode, why you should use something else. So if you're interested in the gory details, go into those. If you want to see things just about the history of cryptography, so if you know the Caesar cipher became the vignette cipher, Cytales, all that history and what's happened throughout the world and how codes have been broken and all those stories. Both of these are pretty good books to read if you're interested in that. That's my Twitter, my email, my blog. That is the link to the slides and the code. So again, these slides, and then I've got exactly what you saw on .NET Core 3.5.1. And I've also got the .NET full framework using the latest version 4.8. So you'll find them. You can see some of the differences, again, suffixes and a few small things, but generally the code should look very familiar. So with that, that's all that I had to go over. So if there's any specific questions.
Thank you, Robert.
You're
Any
welcome.
questions, anybody? So maybe we need some time to digest all of these things, especially some part we have to, fit it in our mind. So up until that point, I might want to ask you if I understand something correctly.
Sure.
Let's assume we want to communicate. You want to send me a PDF and you want to send it in an encrypted way. What we could do is actually I could produce a public and a private key, send you the public key. Since asymmetric encryption is kind of expensive to use in a big PDF file, then you could produce a key, symmetrically encrypt the PDF file, use my public key to asymmetrically encrypt the key file you used on the PDF, and then send me both the encrypted PDF and the encrypted key of the PDF. And of course, with my private key, I could decrypt your key and then decrypt the PDF. Would that be a sequence of events, let's say?
That is exactly right. I mean, that is what typically happens for all modern cryptography. Is the symmetric is what's fast and you need to use it because your files are too big. So you have a symmetric key, that's what you want to use, but you use asymmetric so that you can get the key back and forth to each other in a public way. And then the only hole in that whole scheme is I really have to trust that it is your public key, right? That's the only risk. If I have the wrong public key, someone else can get it. But if you gave me your public key in a trusted way, like you handed it to me on a piece of paper and I typed it in, or I pulled it off of your LinkedIn because I knew it used HTTPS, as long as that's solid, you have it absolutely right. That's what you want to do. That's the best way to do it to get your performance and security and the key exchange.
Super, super. Okay, I have a question here from Luca. He says, when hashing passwords, is it considered safe to normalize Unicode first using NFC/NFD? Not sure I understand.
So I'm not sure exactly what they're going after there, but so I don't run, if I take your password, I'm typically not doing any sort of preconditioning of that data before I'm doing the hashing. So if you think about like, I'm thinking of SQL injection attacks and things like that, where I need to normalize or clear the data, so to speak. I've never seen that in all the stuff I've done for cryptography that anybody said there's any reason to like get a safe version of that because it would affect how the hash would work. Again, if I equate it to SQL injection, there's certain characters I have to make sure you're not putting in a SQL query. So that's why I would want to normalize or clear it. I haven't seen anybody talk about that for hashing, if that makes sense.
Okay, okay. Feel free, Luca, to ask anything else if you didn't think this answered your question. We have another question from Asif. I'm sorry if I'm not pronouncing your name correctly. How key exchange happens in asymmetric? Like if we have a SA signed certificates, probably he means how we exchange the safe way the public key.
Yeah, so that part, so if I'm understanding the question right, it comes down to how do I ensure that I get your public key in a way that I can trust? Hopefully
Yes.
that's the question, so I'll
Most
try to answer
probably,
that.
yeah.
Yeah, so people do put it in their email signatures. I wouldn't trust that, right? I mean, email's a postcard, it can get modified. I would never trust that myself. Would I trust if you had your own website as an author that I knew was yours, like you're a popular person, I knew was your blog and you used HTTPS, I would take your public key from that.
Okay.
There are vendors, so I don't get into it here, but when you go download software, you'll often see a unfortunately SHA-1, but hashes of the file. Like here's the distribution to make sure that it hasn't been tampered with if it got hosted somewhere. Here's the key that you should use to check. As long as I'm pulling that from the vendor's site and I trust they haven't been breached, right? I have to have a little trust in that. And they used HTTPS. For major vendors, I would trust that. When it's you and I, so let's say I needed to start getting your public key, it'd be a little hard to figure out how do I for sure know it's you. Like if I did it today, you've got video on, I would say,
yeah.
hold it up on a piece of paper, right?
Here
And
it
I could
is.
try to copy it and hope I copy it right. But then I saw your face. It's back to the nothing's perfect. We've got to do something that's reasonable. I would probably say if I knew your website for sure, or your Twitter or your LinkedIn that I've been talking with you for a long time, I know it's yours. If you had it on their site, I would trust that. If it's anybody else on the call that, I see your name, but I haven't met you and I don't know, anybody could say they're Thomas and send me a URL with a fake public key. So that's still kind of a problem, right? That's what we have to figure out. And some cryptographic systems in the past have had what's called the web of trust, where maybe Thomas, George really well, he could vouch for you, right? You could give me his public key signed by you, and then I would trust it. And that's basically what certificate authorities do, right? They say, you don't know the web server for sure. Certificate authority is vouching for the web server that they hosted something on their domain. So I'm trusting that Let's Encrypt has vetted your website, and therefore I have some level of trust. Not that you're doing everything securely, but at least that you have the right certificate so that it's not being stolen in transit, if that makes sense.
Yep. Yeah, perfectly makes sense. There is another question by Luca, just out of curiosity, as he's stating, what's the difference from a regular PRNG to a cryptographic pseudo-random number?
Okay, so the question...
Does it provide better randomness, right?
Yeah, so the normal random, and I don't remember because I don't even use it in .NET, but there's like random and you pass it 1 to 10 or whatever. Those typically used to get seeded just by like the date time. for instance. They would just look at the clock and say, we're going to use a random seed of the clock. The clock's not very random. If I saw when you sent me the message, I could guess a few of the times, right, close to when you made that file, and I could guess what your seed might have been. So they just, I don't know the details, and I could look into it in .NET Core and the source and see where are they pulling for that the cryptographically strong. Where do they pull the randomness from? I mean, they do some goofy stuff, right, to try to pull random data. Do they access, I don't think they're doing this because it's not on my machine, but like Cloudflare, are they looking into the physical world with lava lamps to get true randomness that's not based on computers? They could do that. In .NET, I don't exactly know the difference between what the weak ones do. I know most of them are just simple time-based. I don't know how crazy they get in their cryptographically strong. That again is just a trust I have to have that they're doing what they need to make it strong enough. But I don't know the details of the .NET one exactly where they pull that entropy or randomness from. But it is, I know it's critical, right? I mean, I know if I'm not using what's considered cryptographically strong, that my random numbers really aren't. And so even, let's say I had a prize, I don't have a prize. If I had a prize and said, I'm going to give it away to somebody here in the session, right? And there's 19 of you, I'll create a random number. I always still use cryptographically strong randomness. I never use the other ones. They shouldn't really be there in my mind. Why wouldn't you, if you're claiming it's random, why wouldn't you make it the best you could? But
yeah, correct. Yeah. Well, randomness is important, if I understood it correctly. So it will forbid you from spotting, let's say, patterns in an encrypted. Yeah.
Yep. I mean, a lot of the systems that have been broken historically have been broken because of not having that randomness. That the mode I showed you in symmetric when I used ECB and I typed in, I'll pop over there quick, but in that symmetric, right, when I did the wrong type, so let me pull that up here quick. Just gonna minimize, pull this out of the way. When I used the wrong mode here, and when I ran that thing was wrong. So again, maybe you're sending enough data, it doesn't matter, but let's say George and I are just deciding, buy that stock or don't, right? He's my stockbroker. If I send you this every day, and I send you no every day, right? And you see me tweet that I just bought Apple yesterday, well, now that yes. So now every other time I communicate with him and send yes, that I'm telling him, yeah, buy that, don't buy that. I mean, that just using the right mode and adding in that randomness now makes it where the person attacking me doesn't get any hint. And that's what I want. I mean, and that's why the more randomness you sprinkle in all of this stuff with cryptography, the harder you raise the bar for the attacker, right? I mean, nothing's impossible, but again, I have locks and fence and a dog in my yard. They're probably not going to steal from my house, right? And they're going to go next door where none of that is. And so that's what I'm hoping for, right? I want to make it hard.
Yep. Yeah, amazing. Any other question, guys?
And if you don't hear, like you said, it's a lot to digest. I understand that. I had to pop through some of the code fast. Reach out to me, right? I mean, I'm available. I'm sitting at home like everybody else, right, during these trying times. So if you have questions about some of the code, feel free to reach out to me, and I'd be glad to help you.
Thank you.
Welcome.
That is very kind of you. Yeah, I think we can end it here, guys. Since it seems there is no other question, Robert, you are free to ask Robert a question. You can add him on Twitter. I think we can, end this very interesting meetup here. Thank you very much, Robert. I really wish we can have you again sometime in the future with us.
You're welcome. That would be fun. I've been to Germany once and I had a really good time, so I'd love to visit again. I appreciate you hosting this, and
that would be amazing. You never know. After the coronavirus times, these weird times, you might visit it and you might have a real life meetup.
Yeah, I do a lot of international travel usually. And so if I'm in that neck of the woods, so we've been to Munich before, years ago, and have been all around, really enjoyed it. My daughter and we were playing in a park, and we turned and looked at my daughter, and she had 2 or 3 new friends she was playing with. She couldn't speak German, and they didn't speak English from what I could tell, but they were having a great time. So maybe one of your kids was playing with my daughter.
You
Who
never know.
knows?
Yeah.
Yeah, but I would love to visit sometime if that's possible, and appreciate you having me.
Perfect. Thank you. Thank you, Robert. People also writing a big thank you to you for the talk and everything. So thank you very much. Really wish we'll see you again in the future. Guys, thank you everyone for being here. I will, as promised, I will upload this session to YouTube so you can check the meetup again, the streaming again. But you can also note down this URL and you can get the slides and the code from Robert. Thank you. Ciao, everybody.
Thanks. See ya.